In the second part of Precalculus Lesson 11, we look at solving polynomial inequalities analytically. This lesson is from section 2.6 in the College Algebra textbook, and I begin by solving 3x squared plus 5x less than 2. The first step would be to get a 0 on the right side of this inequality, so I will subtract 2 from each side. That gives me 3x squared plus 5x minus 2 less than 0. If you remember how we were solving inequalities graphically, what I would have done here is take 3x squared plus 5x minus 2, give it a function name such as f of x, and then I would graph f of x. Right here, I would have, say, y equals f of x, and I would look, in this case, if I'm wanting to know where f of x is less than 0, I would look where the graph is strictly below the x-axis, and that would give me a solution. Now we're going to take a bit different approach. We would still start by getting a 0 on the right side of the inequality, but now I would factor the left side, in this case, into 3x minus 1 times x plus 2, and then I would again name the left side of my inequality f of x, this time in factored form. I would have f of x equals 3x minus 1 times x plus 2. So I'm going to next find the zeros of f of x. The zeros here would be, if I set 3x minus 1 equal to 0, I find that x would be equal to 1/3. If I set x plus 2 equal to 0, I find that x would be equal to negative 2. Note that these zeros correspond to the x-intercepts that we use to solve this inequality through graphing. Well, let's go on, and to find where my function is positive or negative, I'm going to create a number line or a sign chart of sorts. And so I will, on this number line or sign chart, I'm going to put my zeros of negative 2 and 1/3. And these are x values that go along this number line. And so I will actually put the word 0 above negative 2 and the word 0 above 1/3. So I remember what's going on at those 2 points. The solutions to inequalities are generally intervals. And so I'm going to test 3 different intervals here to determine whether those intervals satisfy my inequality or not. And to do that, I can pick any old value I want to in each of these intervals. So let's test maybe in the first interval where I'm to the left of x equals negative 2. Oh, let's choose a test value of maybe x equals negative 4. How I test then is I go back up to this factored form of f of x, and wherever I have x, I'm going to plug in negative 4. Well, 3 times negative 4 minus 1, I don't really care what number it is. I can tell pretty quickly it's going to be negative. And then negative 4 plus 2 would also be negative. So if I take a negative number times a negative number, note that that would be a positive value. So to the left of x equals negative 2, all y values would be positive for this function. Between negative 2 and 1/3, let's test x equals 0. Coming up here and plugging in 0 for x, I have 3 times 0 minus 1 would be negative. 0 plus 2 is positive. Well, a negative number times a positive number is negative. So all y values between x equals negative 2 and x equals 1/3 are negative. Then to the right of 1/3, oh, let's pick x equals 10. Coming up here again to my function, I have 3 times 10 minus 1 would be positive. 10 plus 2 would be positive. Positive number times a positive number is positive. So to the right of x equals 1/3, all of my y values would be positive. So now I look at what am I looking for here? Well, let's get rid of some of this just to clean things up a bit. What am I looking for? I'm looking for where my function is less than 0 or strictly negative. There's only one place that occurs here, and that's between negative 2 and 1/3. That tells me that the solution to this inequality would be negative 2 to 1/3, not including those values of negative 2 and 1/3. So the solution is negative 2 to 1/3, not including the endpoints, and note that that is the same solution we would get from our graph here. Let's look next at solving 2x times x plus 1 times x minus 3 greater than or equal to 0. Well, this is actually an inequality that we already solved graphically, so let's take this new approach. You can see the graphical solution we came up with here to the right. First thing I do then is, this is already factored, so actually I don't need to factor. I would go ahead and just give the expression on the left a polynomial name, or a function name, f of x. So I have f of x equals 2x times x plus 1 times x minus 3. I would then look for the zeros of this function. So my zeros would occur when 2x equals 0. That would give me x equals 0. Also when x plus 1 equals 0, or x equals negative 1, and when x minus 3 equals 0, or x equals 3. So I have my three zeros. I set up a number line or sign chart, and I put on that number line the x value of negative 1, the x value of 0, and the x value of 3. These aren't really uniformly spaced like they usually would be on a number line. They're just there to serve a purpose mostly. So now we're going to test some values in each of these regions after I note that each of these is zeros by writing the word 0 above. That isn't that important here, but when we get to solving rational inequalities, it will be important to note that these are zeros where that occurs. Okay, so to the left of x equals negative 1, let's test, negative 2. So I'm going to come up to my factored version here of f of x, and 2 times negative 2 would be negative. Negative 2 plus 1 is negative. Negative 2 minus 3 is negative. A negative times a negative times a negative would give me negative y values in that region. Between negative 1 and 0, I can test negative 1/2. Coming up here, 2 times negative 1/2 would be negative. Negative 1/2 plus 1 would be positive. Negative 1/2 minus 3 would be negative. So we have a negative times a positive times a negative number resulting in a positive number between x equals negative 1 and 0. Between x equals 0 and 3, we could test x equals 1. Again, coming up to my factored function f of x, plugging in 1. 2 times 1 is positive. 1 plus 1 is positive. 1 minus 3 is negative. So between x equals 0 and x equals 3, we would have negative values. Positive times negative is a negative. Then to the right of 3, I could pick a test value of, let's do 6. Coming up to my function again, 2 times 6 is positive. 6 plus 1 is positive. 6 minus 3 is positive. A positive times a positive times a positive would give me positive y values to the right of x equals 3. Okay, so we get our solution. What are we looking for here? Okay, again, let me erase some of this stuff just to make it a little cleaner here. And what are we looking for? We're looking for where my function f of x is greater than or equal to 0. So I'm looking where the function is greater than 0. I'm looking for positive values of y. Where the function is equal to 0, I'm looking for zeros. So the final result, looking at my number line, going from left to right, I would go from negative 1 to 0, including both of those values, union 3, including 3, to positive infinity. And if you can look at the graph here, we do have the same solution that we came up with through the graphing method. Now let's find the domain of f of x equals the square root of x squared minus 4. So what we need to do here is we need to find values of x for which x squared minus 4 would be greater than or equal to 0. This is something we could not have solved up to this point, where we're learning the methods of solving polynomial inequalities. So once I have x squared minus 4 being greater than or equal to 0, I factor the left side into x minus 2 times x plus 2, and then just like we've been doing, I'm going to call the left side of this inequality f of x. So f of x equals x minus 2 times x plus 2. Then I'll find the zeros, which setting x minus 2 equal to 0 would result in x equals 2. and setting x plus 2 equal to 0 would result in x equals negative 2. So x equals 2 or x equals negative 2 would be my zeros. We go ahead and create a number line or a sign chart here, and we put negative 2 and 2 as zeros on this number line. And then we test the value in each region. So to the left of x equals negative 2, let's try negative 3. So to test x equals negative 3, I'm going to go up to my factored version of f of x, putting negative 3 in for x. I would have negative 3 minus 2, which is negative. Negative 3 plus 2 is negative. A negative number times a negative number would be positive. Then between negative 2 and 2, let's test 0. It's usually the easiest. 0 minus 2 is negative. 0 plus 2 is positive. So a negative times a positive is negative. To the right of 2, let's try 5. 5 minus 2 is positive. 5 plus 2 is positive. So to the right of x equals 2, all of our y values are going to be positive. So we finish off here by, remember, we're solving to find the domain here. So the domain of this inequality, we're looking for where x minus 2 times x plus 2 is greater than or equal to 0. And where that would occur would be where I have pluses here or where I have zeros on the sign chart. And I can write out the solution then, the domain, as negative infinity to negative 2, including negative 2, union 2 to infinity, including 2. And that would be our domain of f of x. Try on your own. Number 2 for this lesson is the height h in feet of a ball above the ground t seconds after being tossed into the air is given by h of t equals negative 16 t squared plus 96t. For what interval of time is the ball more than 128 feet above the ground? This is an application problem, but if you think about it, it's going to be solved through an inequality. So just look at it a minute, figure out what your inequality is, and you can solve it just like we've been doing here.